Hello everyone. This part of the presentation is about the body class. The body class has the source code necessary to populate the body block in WEC Sim's Simulink library. The body class is used to define the attributes necessary to evaluate a body's dynamics in general and hydrodynamics in particular. This slide shows a typical use case scenario, where the body is identified by the user using an HY file which contains all the hydrodynamic coefficients evaluated in a BEM code such as vomit or Capitan. The body's geometry is defined in ASCII.stl format, and the pertinent inertias are defined as inertia matrices. The user can also define bodies that are part of the system but do not have hydrodynamic forces associated with them. An example of such a body would be an anchor or a support structure above the surface of the water. Additionally, the user can define different initial conditions, such as different spatial orientations the body may have. The body class uses properties to define the physical facts such as center of mass, volume, and hydrostatic stiffness. There are certain properties that can be modified by the user so as to customize the simulation for different scenarios. These properties are shown within the green rectangles. The read-only properties are populated using H5 file written by the BEM solvers such as vomit and are inaccessible to the user. The physical facts about the body are then used to evaluate additional attributes necessary to solve for the system dynamics. The methods of the body class are functions that use the known information to evaluate the attributes necessary to initialize the simulation. The methods that are shown in the red rectangles are accessible to the user to probe the existing information or to use the methods to evaluate additional information. However, some of these methods, the so-called private and protected methods, are used to generate information that is typically used by the solver, such as inputs like excitation forces. These methods are effectively hidden from the user. The main reason for this is simplicity, and the user may not really need to define these because these can be calculated a priori simply based on the hydrodynamic coefficients evaluated by BEM solvers such as vomit. There are three different types of body blocks used in WEC Sim: the hydrodynamic body, the non-hydrodynamic body, and the drag body. The relevant body block is selected using the variant subsystem functionality in Simulink. The hydrodynamic body is a body evaluated in a BEM solver such as vomit or Capitan. Such a body has hydrodynamic effects associated with it, and its hydrodynamic coefficients are saved in an H5 file. On the other hand, the non-hydro body is a body that is part of the system and affects the system dynamics, but whose hydrodynamics do not necessarily affect the system dynamics. Do note that the weight and buoyancy of a non-hydro body is still considered. An example of such a body would be an anchor or parts of the system above the surface of the water. Similarly, a drag body is a body whose weight and buoyancy are considered, but hydrodynamics are not considered. For a drag body, however, the drag coefficients can be included in the analysis. Therefore, WEC Sim can incorporate bodies that contribute to the overall system dynamics, but may or may not be subject to hydrodynamic effects. Further, There are two different types of hydrodynamic bodies that can be used in WEC Sim. Typically, a rigid body is used because it has 6 degrees of freedom as defined conventionally for marine systems. However, some systems do require generalized modes that are defined by the user. These are typically used for flexible bodies. Here is a more direct comparison of the 3 different types of body blocks. Notice in the hydrodynamic body column, different hydrodynamic forces can be calculated, such as the excitation force, the radiation force, and the restoration force. However, for a non-hydrodynamic body and a drag body, only the weight and buoyancy are considered. For the drag body, however, drag forces can also be calculated. Here is an exploded view of the hydrodynamic body block. Notice the numbers that are labeled on the lines connecting the different blocks. These numbers correspond to the signal size. The number 6 in the left half of the diagram corresponds to the 6 different modes. 3 in translational directions, namely the surge, the sway, and the heave, and 3 rotational modes, the roll, the pitch, and the yaw. Notice in the right half of the diagram, the lines are thicker between some of the blocks. The thicker lines signify that a bus was defined. In Simulink, buses are used for more efficient routing of signals, so that related signals are clubbed together and they could be used in different parts of the Simulink module more easily. The general equation of motion for a body experiencing hydrodynamic effects is represented using the Cummins equation. The screenshot on the left shows the implementation of Cummins equation in WEC Sim. The different contributing forces are the excitation force, the radiation force, and the hydrostatic restoring force. Additional forces like the Morrison element force, the viscous damping force, and any other linear damping force can also be included. The screenshot on the right shows the calculation for excitation force on the system. The excitation forces on the body are calculated using the convolution integral of the wave elevations eta and the excitation force impulse response function hf. This is shown in the bottom equation. A more explicit implementation is shown on the top equation, where the right half of the right side, on the right side, the term after the integration sign, square root of 2 times s times d omega, corresponds to the wave elevation time history, where s is the spectral density of the incoming wave. The term fx times e raised to the power iota times omega t plus phi corresponds to the Fourier transform, which converts the excitation force coefficients in frequency domain as calculated by BEM software to the excitation force impulse response function as represented by HF in the second equation. As the body moves, it radiates out energy, which can be modeled as a combination of an inertia term, the so-called added mass, and a damping term, commonly referred to as radiation damping. The forces corresponding to the frequency-dependent part of the radiated energy need to be Fourier transformed so that the radiation forces can be calculated in time domain. The Fourier transform of the frequency-dependent part is known as the radiation impulse response function. In the equations below, the second term shows the convolution of the radiation impulse response function and the body velocity. For a regular wave, this convolution simplifies to a simple multiplication because the incoming wave has only one frequency. However, control design and computational costs can be significantly facilitated if this convolution integral is replaced by a linear time invariant system such as a transfer function or a state space model. WEC Sim performs iterative system identification in the Bemea routine to estimate an equivalent state space model that can replace the convolution operation. In the rightmost screenshot, three variant subsystems are shown, corresponding to 1. Regular waves, where the convolution reduces to a scalar being multiplied to the body velocity at each time step, where the scalar is the radiation damping at the pertinent time step, corresponding to the pertinent incoming wave frequency. Second is the case with irregular waves, where the convolution between the radiation impulse response function and the body velocity are evaluated at each time step. And third, where the state space model is used to circumspect the convolution. The screenshot on the right shows the implementation of viscous damping forces and the Morrison element forces. These forces correspond to the viscous forces acting on the body. These are a function of the damping coefficients and the velocity of the body. The corresponding equations are shown at the bottom of the slide. Here is the culmination of all the force calculations that were discussed in previous slides. The green total force block on the left brings in the summation of all the forces that were calculated previously. These forces are exerted on the body using the external force block. The external force block only takes in the external force block takes in the translational forces and the torques separately, and that is the reason the selector blocks were necessary. The selector blocks between the total force block and the external force block bifurcate the 6-mode total force signal so that the top line selects the translational modes, the surge, the sway, and the heave, and the bottom line selects the rotational modes, the roll, the pitch, and the yaw. The blue block at the bottom is a motion sensor, and it logs all the forces experienced and exerted by the body. The two rigid body blocks at the top right ensure that the body's location, orientation, and center of gravity were correctly ensured. These are very important for modularity of WEC Sim because they ensure that spatial and force relationships between different bodies are correctly defined. The force relationships are usually defined using the PTO blocks. These rigid transform blocks make sure that the follower and the base, i.e. the relationships defining which body is reciprocating with respect to whom, are correctly defined. To summarize, in order to simulate a body in WEC Sim, our user needs to define the body as a body class object. This body class object can be a hydrodynamic body, in which case the hydrodynamic coefficients are necessary, or it could be a non-hydro or a drag body, in which case the hydrodynamic coefficients are not necessary. In either case, the user needs to define the inertia matrices and if any initial displacements or changes in orientations are necessary. Once the body object is correctly defined, the wave class or the wave information is correctly defined, and the corresponding relationships between the bodies through the PTO and the constraint blocks as defined, the WEC Sim simulation can be completed. Thank you.